Hi everyone, welcome back to the channel. So last time we completed with the Leetcode bi-weekly, like all the four problems. Today let's start with the weekly contest that happened last week and go from fourth problem to third and so on till first. So in this particular video, we'll be covering the fourth problem, which was kind of like a very tough problem. Very few people solved it, like about I think 200, 150, 200 people did solve it. So yeah, let's look at the problem, the brute force, the optimization, and most importantly, how that optimization works in the given time constraint. So in this particular problem, it was slightly deceptive. The time complexity was not apparent. So although it looked like the brute force is passing, but in fact it was proper optimization, and because of certain reasons, the complexity was within the limit, right? So let's go ahead, let's take a look at the problem first. Okay, so this problem goes like this. It says you are given a string s and an integer k. So two things, a string and an integer k. What you need to do is you need to first of all start at the beginning, choose the longest prefix of s containing at most k distinct characters. So for example, if k is 2, that means we can just keep two distinct characters. So we can keep the entire string in one, right? But let's take another example where it would be much more clear, right? So for example, in this only, we had instead of a triple c a, we had a c c b c a. So what would happen if I start taking prefix? I get one unique character a, then another unique character c. C is still there, so it's still two unique characters. As soon as I try to take b, the number of unique character become 3, which is more than this k. So this is not a prefix that I can take. So I have to take the longest prefix that contains at most k characters, k distinct characters, and we are deleting that prefix from the entire array. So if I go about doing this here for k equal to 2, what we will see end up happening, we'll start at the beginning, we'll do acc, this is the only prefix we can take, we cannot take b, and we'll delete it, so we'll get bca. Then we start at b, we take b, we take c, we already have two distinct characters, we cannot take a, so we'll delete bc, we'll be left with a. And finally a would be deleted because it's having at most k unique characters. So we'll have to do the operation thrice. Remember, we are always taking the longest prefix. If we had to actually maximize the number of deletions, we could have tried taking only ac, but that is not allowed in the question. It says you have to take the longest prefix having k distinct characters. Okay, now what you need to do, so what they have done is called each of this as a partition. So acc was one partition, BC was second partition, A was the third partition. Now, the operation that you can do is you can choose any one character and change it to any other character in the world, right? So for example, if I decide I'll take this C and let's say change it to D. And you have to do it in such a way that you maximize the number of new partitions that are there, right? So as an example, let's say this was instead of just A, it was AE. So now I had, like earlier in the string, I had ACC as one partition, BC as another, and AE as another. If I change this C to D, let's see what ends up happening. So our string becomes ADC, BC, AE. So in this case, with K equal to 2, I'll have to take AD as a only prefix. I cannot take C now. Then take CB as the next prefix, and then take CA as the next prefix. Okay, yeah, I can actually take CBC. So probably not the best example here. So probably instead of this C, let's say we had F. Okay. Yeah, so it would not have been CB, but actually CBC, right? So just to avoid that, I've changed that second C to F. So now we have AD as a separate, CB as a separate. Now I'll have FA as the third and E as the fourth. So basically you want to change a character so that you can maximize the number of partitions that you create, right? And you can just do one operation. You can just make one change that is out there. Okay. So that is what the question says. It seems like a super simple problem, ideally. Like, why would you even tag it hard? Because it seems like, yeah, we can only increase the partition by one. So we just have to calculate if it will remain same or it will increase by one, something like that, right? But Actually, when you start diving deep into it, you'll see that the problem is a lot more complex. Okay. So at this moment, I would want you to pause the video for a moment and think if you can come up with a brute force solution at least to this. Okay. So let's go ahead and discuss the simple brute force solution. So before that, what I'll do is I'll go to the constraints ones and quickly show you the constraints for this problem. So this problem says, first of all, S will only have lowercase English characters. So a good point to note here, that number of distinct characters in S is just going to be 26 because we just have 26 characters in our English alphabet. So just 26 is going to be the number of distinct characters in S. Second, it says length of the string is 10 to the power 4. So S dot size can at max go up to 10 to the power 4, which is your N also for most problems. And lastly, K can go up to 26, which again makes sense because even if it's more than 26, you're actually allowing all the 26 characters to occur, right? So yeah, so basically K, even if it was more, it would not have actually mattered. Cool. Can you first calculate the answer for K equal to 26? I think everyone would be able to do that, right? So just pause the video for the moment and think about K equal to 26 case. Can you directly tell what the answer would be? Okay, great if you were able to think. So answer is going to just be 1 because no matter what changes you bring, they're all going to be within the 26 distinct characters of English. So the entire string is going to always be one partition, right? You can keep on taking all the characters and you'll never be able to make a single partition because it is increasing the limit of number of distinct characters, right? So yeah. Okay, so k equal to 26 is a trivial case. We can write it as a if we want, but let's try to solve it in a general scenario as well. Cool. Now let's go to our board and let's think about our brute force. Okay. So the absolute brute force that comes to the mind is, let's say we are given a string A, B, C, D. Let's take some more repeated characters C, A, right? This kind of a string. So what I can try doing is, if I look at it, how many different possible strings I can actually create by making just one change, right? So if I look at this A, I can replace it with B, C, D up to Z. So I can make 25 changes to the first character. Similarly, I can make 25 changes to the second character. So plus 25. Similarly, third, fourth, and last characters. So the number of new strings that I create by using that operation, what was that single operation? Take any character and change it to any other character. So that is just going to be 25 into n. Or for the sake of simplicity, we can take it 26 into n because yeah, at the end of the day, it just represents all the characters. So in our brute force, we would not want additional complexity of checking. We should not change a to a, right? We can keep changing a to a also. So just allow 26 into n. Cool. So I can make 26 into n different possible strings by my operations. And for each of them, I just need to check what is the number of partitions that I'm going to create, right? So how can we check that? That is relatively simple. We can keep on taking the characters. We take A, we take C, we take A. So let's say K is 2. As soon as we get a character for which it is a new character, let's say we are using a set or an array to store what characters are already there. Whenever there is a new character and it increases the limit of k in terms of distinct characters. So for example, right now the distinct characters were just 2 and now b comes and this distinct character will increase to 3. So as soon as this is going to happen, we'll do a count plus plus and start a new partition here. So just in a loop of O of n, taking character one by one, noting down the distinct characters, and whenever the size is going to increase beyond k, starting a new partition there and increasing the number of partitions by 1, we can actually achieve for a particular string how many partitions would be actually there, right? So what we can do, we can generate all these 26 into n strings and for each of them do an operation of n to know the number of partitions and find the minimum out of it. So just to take as an example, what we can do, let's say our string was just ABC, or let's say ABA. Now what we can do, we can try changing this character. So we'll generate strings like BBA, CBA, DBA up to ZBA. Then change B, so we'll create something like AAA, ACA, so on and so forth, right? And similarly change the last A, right? So generate all these possible strings, which would be just 26, because every character can be replaced by 26 alternatives, into n. Generate all of these strings. Remember, you can just do one operation, not multiple. So it cannot be that you change A also, you change B also. So it's not 26 into 26. Like, you generate the string with this is 26 options, or you replace B and you generate next 26 options, right? So it's plus and not multiply. If you're not familiar with this concept, just read about product rule versus sum rule, which is a common rule on to decide when you multiply the choices and when you add choices, right? So yeah, this is basically comes under sum rule, because we have or. Either this could be a possible way to generate choices, or this could be a possible way to generate choices, right? So basically, yeah, 26 for this, 26 for this, 26 for this. So 26 into n strings we generate, and for each string we do an on operation to actually figure out how many partitions are there and take maximum out of the results of all of them. Yeah. So we are able to write a simple 26 into n square approach, right? So if you even have to code it out, it would simply go like this, like for I equal to 0, I less than s dot size, I plus plus. I replace s of I by 1 all the characters. So a loop for character c equal to a, c goes to z, and then replace s of I with c, calculate the answer for it, store it in the max, and then replace it back with the old value in c, s of I, right? So just probably store the old value and replace it after the calculation. Partition function would simply look, let's take a set, keep on putting elements. As soon as a new element comes, set size is already k, and a new element comes which is new, right? It's new. So we have to start a new partition. We can clear the set and count the number of partitions by 1. So yeah, I'll show across the code for partition if you want. Yeah, this is the brute force that I tried during the contest as well, and I tried to optimize it a bit using some computations. So for example, what I did was to remove the factor of this 26. I would say that, for example, if I want to replace this A, it doesn't make sense to replace it with B, because it is going to get together with one of the given other characters, right? So it's better to replace it with something which is as far as possible from it. So what I tried doing is I tried to find for each character which is the character which is the farthest from it, and only replace it with that. So with that I was able to reduce it to 20 by a factor of 26 and into on square. But even on square for 10 to the power 4, which is 10 to the power 8, did not seem to pass during the contest. I thought that 10 to the power 8 is sufficient, because 10 to the power 8 is kind of like the borderline. But yeah, basically did not pass the test cases, because they wanted something of around linear complexity, and that we'll see next. Okay, great. So I would seriously advise everyone to implement this brute force, because this is not as trivial as a general brute force is, right? And then only proceed with the optimized solution. Okay, let's move to the optimized solution. Okay, so for that, first I would like to introduce to you the concept of Bitset and what is the idea behind it. So I'll take a small example. Let's say we have 5 things with us. Let's call them A, B, C, D, E, right? And let's say there are some operations coming which say you include A, you include B in your set, you remove B from your set, you remove A from your set. So some addition operations and some deletion operations. Okay. Now, what do you want to do? You want to tell your size of the set after every operation. So one simple way is we can use our unordered or ordered set that we already know. Whenever A comes, we put A into the set. Whenever B comes, we put B into the set. Whenever we say delete, we remove that from the set. And we can simply return the size of the set, and that should be sufficient enough, right? Another way to compress this information further. So when we are using set, we are actually storing the elements A, B, C, right? So whatever the size of the element is into the size of the set, that much complexity we are storing in terms of space. Instead of that, what we do is we represent each of our thing that is there as form of a bit. So initially, none of the five things are in our set. So the value is 0. 0 means 0, 0, 0, 0, 0, like 5 times 0. Okay. Now let's say I introduce A into the set. I say I need to include it. And let's say its position is the fifth position. So I'll change this bit set into 1, 0, 0, 0, 0. So if you are familiar with bit manipulation, what is this number? Quickly try to calculate. So it is 2 to the power 0, 1, 2, 3, 4, 2 to the power 4. What is 2 to the power 4? 16, right? So 16 actually represents 1 followed by 4, 0. That means A is there in the set, B, C, D, E are not there in the set. Now let's say I try to add seed also to the set. So what will happen? I'll say that, okay, C's position is position number 2, and I just need to add 1 there. So I'll say 1, 0, 1, 0, 0, which becomes 16 plus this is what? 4, so 20. So 20 represents the set where A and C are there currently. Okay. Now let's say I want to remove A. So what do? I change this to 0. So 0, 0, 1, 0, 0. So now our 4 represents only C. So if the number of items that are there in the set are less, are very less, you can actually represent them as an integer or a long by this idea of bit set. So this is the idea of bit set, that for every item you allocate a bit, right? Whenever you want to include that item, how do you go about it? Whatever the current bit set is, let's say that is S, you take OR, bitwise OR, with 2 raised to the power the index of that item. So for example, index of our C was 2. So index of our C was 0, 1, 2. So actually if we take OR with 1 to the power 2, here whether there was 0 or there was 1, we would replace it with 1. So yeah, OR, bitwise OR operation here helps a lot, right? So whenever you want to include an item in the set, you just do new bit set is equal to old bit set or 2 to the power the index of the item. Okay. What if you want to remove? Let's say you want to remove. So when you want to remove, first you check if that item is there or not. So you take AND there. So if that item is not there, so this is basically for checking. If that item is not there, then when you take AND, then this number has 0 at all the other places. If this number has a 0 at the place where we are putting 1, right? For example, in this particular scenario, let's say D's position is 2. If I try to take AND of this number, this 10100, with 2 to the power 1, which is its position, so it would be like taking AND with 00010. So actually it will end up becoming 0. So if this AND is 0, that means this item number index is not there in the set. And if this AND is not 0, that means this item is there in the set, right? So this is for checking. And when you want to remove it, if you have checked it already, you can take XOR because it will have 1. So 1 will be changed to 0 because of this XOR. When we add another 1 to it via XOR, then it will become 0. So we in a way reduce addition, deletion, checking these operation with simply bitwise operator of OR and XOR. Last thing, if we want to check how many elements are there, so count the number of elements are there, then it can simply be written as bit count or pop count or bit count, number of set bits in our bit set. So that is the main idea of bit set structure. Whenever you have less items, you represent each item by a bit in your number, either an integer or a long number. Whenever you are including an item, you just take OR with 2 to the power that position, so that position becomes 1. Whenever you are checking, you just take AND with 2 to the power that position, so that if it's 0, that means that item was not there. If it's not 0, that item was there. Lastly, if you want to remove that item, you take XOR, because if it was there, then it will change it to 0. And lastly, if you want to count, just count the number of set bits. Okay. So this idea of bit set actually helped a lot in this particular problem, because we just had 26 characters and we just wanted to know whether they are there or not. We want to include them at times. Whenever we are adding a new element, we want to include this new character in the set per se. And whenever we wanted to count, we just wanted to count, right? How many actual elements are there currently in the set to compare it with k. So this bit set data structure actually became very important while we solved this particular problem. Okay, let's use this concept to actually define how we solve this problem. So initially, if we think about it, let's say our string is A, B, C, B, C, A, and K is 2. What we do? We start making partitions. So let's forget about right now the change that we want to bring about, right? Let's try to calculate partition with the new way. So what will we do? We'll take A. So our string becomes 001. So I'm assuming that A is actually at the first bit, then B, then C. D, F up to Z I have ignored because my current string only contains ABC, right? So yeah, we include A. So this becomes 001. Then I include another A. It becomes 001. If I check how many bits are set, it's just going to be 1, because right now we just have included A in our set. Now I take B, it becomes 011. If I count the number of bits here, it becomes 2. Now when I try to take C, I'll see that, okay, taking OR with 2 to the power 012, right, 2 to the power 2, this thing will have, if I take bit count, this thing will have the number of bits greater than k. That means this C cannot be included now in the same set. I need to start a new partition. So I'll again change it to 0, 0, 0, and start by putting C as the first element there, counting this as one partition. Partition becomes 1. So replacing the same idea of our brute force with not a set but a bit set, right? So if you have written the brute force, the next step that I would advise is to change it to a bit set. Remember, we are dealing with 2 to the power 27. So we have to use long. We cannot rely on int, right? Because it would go beyond int. So just have long here. Okay. Cool. So now that we have this solution via bit count, further we can try to optimize it with the help of our recursion and our DP. So let's think about that now. Okay. So let's say again we have our string as this, right? And we want to change just one of them so that k equal to 2 maximizes. Okay, cool. So if you think about what are the options at each place right now. So let's say we are at index 0. Currently our bit set is also 0 because we have not included any element, and we can change one character. So can we change? Let's make a fact can change. That is true. We can change one character. So our options are let A be as it is. That is one option, right? If I let A be as it is, it will become I equal to 1. We go to the first bit set. index, which is B. We make our bit set as 1 because we take OR with A's position, so our bit set becomes 1. And our can change is still true because we have not made a change yet. Other option is we change it with the other characters. We change it with B, we change it with C, we change it with D, so on and so forth, right? So if I change it with B, it would look like, okay, I equal to 1, we are going to S is 2, right? S is 2 because we are now setting the bit for B and not for A. And we cannot make another change now, so we change it to false. So recursion would be like, if you are at some index, some bit set, and some you would say can choose, either you take the same element. If you are taking the same element, you just include it in the bit set and move on. If you are changing that character to a new character, then you make another call, take that new character that you are taking. So maybe run a loop to take B, to take C, to take D, all the 26 options. Try to take all of them, made the changes in the set according to that, and now set the flag to false because now we cannot bring about another change later while we are recursing. Another thing to note in mind, when you are updating set, before updating set, you need to check if taking this element will start a new partition. If it starts a new partition, then you actually make the new recursive call with only that new element, right? And whatever the answer is returned, you add 1 to it, right? So yeah, that is how the recursion can be structured. So probably best would be if I talk about it with the help of the code example directly. So let's go ahead and look at only the recursion part. Forget about the DP for now. DP is like relatively simple always. Like whenever you see overlapping problems, you just memorize it, right? And that is what exactly I also did here. Let me go ahead, go to submissions and go to my accepted one. Okay, maybe copy it and bring it here. Okay, so as I said, let's forget about the DP part for now. So even if you want, I'll comment this out. This is the DP part and this setting is the DP part, right? So what I've done, let's just look at that. So if you see, I have three things: my index, the index that I'm currently on, my bit set that I'm using, and the can change flag. Rest of the things K and S are stagnant, like they don't actually change, right? So three important parts here: the index that I'm on, the bit set of the elements that I've included, and the can change flag, right? So first thing, if you see, I'm trying to take this element as it is. So I'm checking if in this bit set I try to include my current character. So I'm doing s of index minus a because the s guys will subtract and I'll get the index, right? So if I try to, and I'm using or for including that in the bit set, right? So if I include my current character into the bit set and count the number of set bits in it, if that is less than equal to k, that means I can include this safely. Then I just need to make a recursive call for index plus 1, including this into the set with the same can change flag. So nothing changes, just we add the current element into the bit set and increase the index by 1. Otherwise, if including this character takes our number of set bits to greater than k, that means including this character is not allowed in the current partition. So we make a new partition. For that I have 1 plus because this entire thing became a new partition now. And I'll recurse for the next part with just that single character that we have included right now. So I'll make a recursive call for index plus 1 by just including my current character because everything before it that came has become one partition. I cannot include this in the same partition. So I'm just including the current character into that partition. So these two call depending upon whether we can do it with the same partition or whether we want to start a new partition here. Okay, so that is the first part. Now, if can change flag is true, that means we can change this character to the remaining characters B, C, D, E, all of them one by one, and try to include those instead of the current character. So that is what I have done. I have written loop char c equal to A to Z and written the exact same thing here, that if including the current character is safe in the same partition, just make a call. The difference is false. Here, I just propagated the can change flag as it is. Here, can change flag has to become false because it was true earlier and we have made a change, and that is why this becomes false. Okay. Another thing to note here, I am not including s of I. I am including the current character which I am changing it with, right? So this for loop essentially tries to change the current character to all the other characters and make calls for them. Okay. So this was the simple recursive solution. So if I think about the time complexity of this recursive solution, let's see what is happening. Let's go back here. Let's talk about the time complexity of doing this. So if you actually think about it, from every node, we are having one option of no change and 26 other options by making the change, right? So if you actually think about it, from every node, we have 27 options, and you may think that the complexity is 27 to the power n. But actually, practically, it would be much less than that because all of these 26 branches would simply go up to end because we have made one change. We'll not be able to fork other branches from there. Like they'll have to just continue with the same value. Like the if change flag will never be true again, right? This branch will only fork further to 27. Again, these 27 will go directly. This one will again fork to 27. So practically speaking, the number of branches are actually going to be much less than this 27 to the power n, but still they are going to be significant amount of number. Okay. Next thing to note, we obviously will have overlapping subproblems, right? So it can very well happen that we arrive at the same node. So as an example, if we are starting with, let's say, yeah, A, B, C and K is 3, right? So when we reach here, or let's take A, B, C. When we reach here, if we have changed this A to B or this A to B, both of these branches, right? This can very well happen. In one case, what we can do, we can change the first A to B and include it, and then A include, then B include, then C include, right? So this would be one partition. Whereas the other case, we take A as it is, first A as it is, but change the second A to B. Both of these branches will actually go up to here with the same bit set, right? With the same state. Index would be same, bit set would also be same. Can change will also be false because we have brought about a change in both the cases, right? So there would obviously be overlapping subproblems that we can avoid by using dynamic programming. So let's look at the dynamic programming approach as well. So what I have done here, very simple idea. I have made a map from a pair of int, long, long and bool, which is our index, our bit set, our can change. So three things to an int to store the corresponding values. So if I see in my DP, I already have the value calculated for this state. Remember, S and K need not be in state because they are constant. They are not changing. So they need not be in state. So the variables that are changing, they are part of the state. So if DP already has the answer for this particular state, we'll directly return it. Otherwise, Otherwise, what we'll do, we'll calculate the answer and before returning, we'll just store it in the state so that later if we arrive at the same state, we are able to directly return the answer. So classic case of memoization where we store it as form of a map. Why map? Because we are having long, long and those kind of things. So making an array does not make sense, right? Traditionally, we do DP with array, but right now, like it's best to use map because we have bool, long, long, int, all those kind of secondary data types. Cool. So this seems like this actually was a shocking news to me also, that this code actually worked, but you need to do a lot of computation to actually come up with the idea that why this fits into the time complexity. Because on the face of it, it looks like we have n possible indices. At each index, we can have all the possible bit counts, so bit sets. So if I talk about 26 characters, then it could be 2 to the power 26 different possible combinations of bit set, and into 2, because can change can be true or false. So ideally it looks like this map is huge and it will never fit into the time complexity because we are having 2 to the power 26. But actually you will end up seeing that the complexity is very less compared to this, and this is a classic case of sparse DP. So, like generally, the DP that we see in the world is continuous DP, right? For any calculation, we pretty much have all the states there, right? We'll directly calculate with the previous state, right? And we end up filling the entire table. But here specifically, it's a sparse DP. Only some of the you can say states actually have solutions. Rest of the states are even impossible. So they are not going to be there in the map itself, right? So this is the case of sparse DP. Secondly, this is the Bitmask DP because we are using Bitset. So it's a Bitmask DP. So that is why this was a very tough problem, because A, it was a Bitmask DP, which is already a very less used concept with bitsets, and B, it was a sparse DP. So ideally, if you make a DP, you think that all the states are there, right? But you don't go into the nitty gritties of trying to prove if there could be lesser number of states. So let's just exactly do that. Let's try to figure out why the sparse DP will have very less states comparatively, right? Okay. So let's go back to our whiteboard and prove that out. I think this is going to be the last segment. Okay. Let's say we are at any particular index in our string. So let's say there is a huge string, right? Let's say we are at this particular index. Now, let's try to figure out what are the possible states at this particular index. So at any particular index, if we know the number of possible states, we can just multiply it with n to get the total number of states, right? So we have two options. Either can change is true or can change is false. Let's take the easier case first, when can change is true. Okay. When can change is true here, that means none of the previous characters have been touched as of now. If any of those characters would have been changed, then the can change would have been false. So if can change is true, it will almost always, like not almost always, it will always be true that we have a defined string, only one string, and the bit set at this current position is going to be just one possible scenario, right? There cannot be any other bit set. Like for example, if k is 2, this would be our first partition always. Then at this point when I reach, I will just have b in my bit set. So my bit set would look something like this. And this has to be true because none of the other characters have been changed. So for case true, we just have one possible state for this given index. Let's talk about the more complicated case of false, when one of the previous character has been changed. Okay. So for that, what I'll do is I'll try to go back, like try to look back from this particular character C and see when all we get changes into the bit set. So let me take the false case separately. Let's say we are at some character D, right? The value is D. So if I try to go back and check the substring that has been part of this partition, there is a possibility that there are some other Ds, right? So till I get just only D, there will be only one character in the one in the bit set that is going to be for the bit of D. Rest everything will be 0, right? Okay, only one character D as 1. Now, if there were some more character here, let's say C comes, which is a new character. So till the time only D and C are there, my bit set would look like only D and C have 1, rest everything has a 0. Then when there is a third character also, let's say A, then only those three will have 1 and rest all will have 0. So in a way, if I don't tamper the string, I can say that if I look back, there are defined 26 possible strings, 26 possible bit sets that can be there, right? So for example, like by that I mean, when I'm going back from here looking at the partition, if there is only one single element in the partition, it has to be D, right? So the bit set for a single character has to be 000, only one for D and rest all 0. If I look for two characters without any change, I've not made a change into the character as of now. If I look for just two characters in my set, then they have to be D and C. Just these two. They cannot be anything else because all of the other come later into the picture. So the bit set there has to be when D and C are 1. Rest all is 0. If I go even further, take the bucket of three characters being in our bit set, then they have to be D, C and A. Remember, we are not making a change, right? Okay. Now, I can arrive at this D with at most one change in the past, right? And that one change would be equivalent to taking one of the bits out of these possible scenarios and removing one bit and adding some other bit instead of it, right? So if I look at the number of buckets, if I keep going back, so there is one possible bucket for only single bit, which is just having one for D. Then if I go further back, it would be CD, that is the other set possible. Going back, it could be ACD, right? So in total, I can take all the 26 characters. So I might have sets like D only, then only CD, then ACD, then probably next character to encounter is E, so it would be EACD, right? So similarly, I can just have 26 options. Last option would be when all the characters are there in the set, right? Just 26 options. Out of these 26 options, if I think about it, what I might have done is taken one character out and put another character in. So for example, in this EACD set, what I might have done is I have removed an A probably and added something else in terms of it, right? So let's say I have removed an A and added just F. Or I might not have removed anything because A might have multiple occurrences. So I've just removed one of them. So A is still in the set, but I've just added F. But in total, if we think about it, there are 26 such sets having one character, two character, three character, four character up to 26 characters. In each of the set, I can make one change, assuming that that is the set that we arrive with at D. We can remove one character from there, possibly. So we have option of removing one of the characters, which is 26, and we can add one more new character if we are replacing. So into 26. So in total, the number of possible bit sets with which I can arrive at this D is just 26 cube, because we'll take one of the states which was already there without any change and make a change there. So if we take one of the state which was already there, let's say that is this state EACD that we are arriving at. So we possibly might have added a character like F and possibly might have removed a character. So into 26 options to remove a character, worst case, and 26 options to add a character. So 26 cube are the maximum states, bit set states, with which we can arrive at this D with can change as false. Okay. So basically, if we think about it, the number of possible states for true was just 1, for false is 26 cube. So the complexity in turn, or the number of states possible, becomes 26 cube into n. And that is why this was a sparse DP and our solution could actually pass. Great. Although sparse DP is rare, but some of the good things to take from here are: one, bit set, right? So we have our bit set. So bit set data structure, when it can be used, when we have a few things in our set that we want to continuously add, remove, find out if they're there or not, or maybe get the size, right? So as long as we have few things only, we can represent it as not a set, but an int or a long. Okay. So this bitset data structure is very helpful in a lot of problems. Generally hard problems, generally doesn't come in easier problems. Second, whenever we are memoizing, if there is a chance that only a few of the states are there, which is kind of like a sparse DP, it is a good idea to use a map instead of an array. Because if less states are coming, even if you have an intuition that less states would be coming, then also you could have solved this problem, right? Even if you couldn't arrive with this proof, you could have actually solved the problem by just putting using a map, because if there are less states, automatically less states would be populated and your solution will get accepted, right? So for DP we can use a map, specifically if we suspect that there could be sparse or basically only a few of the states which are actually possible. Cool. So that is the major idea, I think, with this particular problem. Third, that I would say is always look at smaller constraints. There is a reason for which they are smaller constraints, right? So, as an example here, we had yeah, 10 to the power 4. So, although 10 to the power 4 was not to get 10 to the power 8 accepted, but it was because there could be a larger constant with it, which is 26 cube, which is actually in fact a large constant. If it was 10 to the power 5, again things might not have worked with 26 cube, right? So whenever there is a smaller constraint, there is a high chance that the algorithm which is expected revolves around that. Okay. Great. So if you understood this problem, or even if you couldn't, just ask away again in the comments. I'll be happy to oblige and answer all the comments, right? And do code this out. I would advise to code first the brute force, change it with bitset instead of a normal set so that you can get a practice of bitset, and then go on and code the recursion with the DP, right? So yeah, I'll post the comments also in the comment section or the description, right? So yeah, if you like the video, do give it a like and subscribe to the channel, right? And see you guys next, where we solve some easier problems from this contest, starting with the third one.